Chapter 6, Permitting, Encouraging, and Provoking Errors. What I want to do now is give a summary of what we've covered so far in the course. So the first 5 chapters have sort of led up to some conclusions about what engineering ethics is. And then in this chapter, we really want to talk about why it's important to study ethics at all. So what we're doing here is showing that the study of ethics can have some positive impact on the practice of engineering. So what do we know so far? One, we've established that design problems are open-ended. In other words, the problems themselves do not give us a specific design solution or provide a specific design solution. Design problems leave conceptual space for value judgments. So while design problems tell us what needs to be done, it gives us some sort of goal. There is built into that a number of conceptual spaces that we can use to sort of impart our own values into a design. An engineer could solve a problem with an error-provocative design. So we've noted that when someone goes to solve a design problem, one of the things that can occur if an engineer is not careful is that the design could be error-provocative. Error-provocative designs, once realized in artifacts, can cause great harm. So there's a moral component in the design itself and the value judgments that are made when we're designing and the conceptual spaces, but there's also the possibility that once a design is recognized or is realized in an artifact, that these artifacts can cause great harm. Engineers make moral judgments, even if unconsciously, by choosing not to design artifacts that will provoke error. So we can say of engineers that even if they lack the intent to do wrong, they can still do wrong. And in many cases, in fact, probably most cases, engineers make the moral judgment not to design an artifact that will provoke error. Finally, engineers are morally responsible for the choices they make, whether intentional or not. So here again, going back to the previous chapter, when we talk about intentionality and moral responsibility, do I have to intend to do wrong to be held morally responsible? Well, the argument goes that no, you don't have to be intentionally or intend to do harm to still be said to be morally responsible. Again, that goes back to the idea that engineers are professionals and have professional responsibility, and that in relations with others that are taken on voluntarily, that these also generate moral responsibilities, which don't depend on one's intent to do harm. So then why ethics? I mean, as the book notes, when we're talking about engineers, we don't think most engineers are evil. So what's the purpose of studying ethics? In other words, it's most of the case, if engineers are not evil, and we're assuming that engineers who are evil aren't evil simply because they failed to take an ethics class. I don't think anyone's going to argue that. Then the question is, what are we going to accomplish by studying engineering ethics? Isn't it the case that the vast majority of engineers want to do good, that they don't want to create artifacts that provoke error? So what we want to do is go through and sort of give, in some ways, a justification for everything we've done up to this point. What's the point in studying ethics? What's the point in studying these various cases? How can this help an engineer to be more ethical? And we're going to look at questions that revolve around 3 areas of engineering that we've talked about the entire class. So issues in design, issues with regard to harm, and issues with regard to solutions. So one of the things that it's possible that studying ethics can do for the engineer is help them to determine or to answer the question, what counts as a design problem? Right? What counts as a bad design? So if engineers look at their solutions to design problems as making moral choices, they can see problems they might not otherwise see. Awareness of past design problems raises awareness. So one thing that the study of engineering ethics can do is to point out things you might not have thought about as an engineer. After all, as I've probably mentioned before, when the study of engineering, in fact, the reason you're probably taking an online engineering course is that your schedule is so packed with engineering courses and math courses and science courses that there isn't much time to think about these other sorts of issues. So your calculus classes, your statics or dynamics classes, differential equations, you're taking your circuits class or your programming class. And all of these things are very technical oriented. There's a right and wrong answer in all of these things, right? So there's either you got the right answer, you didn't. Either the program works or it doesn't. Either you followed the correct formula or you didn't. So when you're focused only on the technical aspects of engineering, you might miss the fact that what you're engaging in is in a creative endeavor, an endeavor that's value laden. So simply looking at the cases just simply raises awareness, just making you aware of the fact that these can be issues in the solving of an engineering problem. Another way that the study of ethics helps us in engineering is when we ask the question of what counts as a harm. Now, I'll be looking at in greater detail in Chapter 8 as to the nature of harm, what counts as a harm, what counts as a major harm, minor harm, those sorts of questions. So we'll leave for that discussion later in the term, but one of the things that ethics does is allow us to ask the question as to what does it mean to harm someone, and what ways can we harm people or even a community. So the design process is not limited to determining how something should be designed to be used properly. Other harms matter as well. So what are some of these harms? Well, some of these we've talked about, we've seen as we've gone throughout the book. The materials used. How do the materials used affect well-being? This could be something like environmental well-being or community well-being. Energy. How much energy are we using? Where's the source of the energy? Is there a more efficient way to design or to build the artifact that's been designed? And of course, energy, as energy consumption and energy generation has become a major issue, this is something that all engineers should be considering when they're designing artifacts. The time involved. So in some ways, the time either in the use of the artifact or the creation of the artifact, time is in some ways not only money, but is actually a portion of people's lives. So when I buy a product, that money comes normally from my labor of some sort. So whether you're a university professor or an engineer or a carpenter, your skills, your time is transferred or translated into money, and that money is then used to buy things. And so time, there's a number of ways in which time is a factor when we're talking about harm. If I put a portion of my life into my work, I make money, and then I buy an artifact that's defective in some way, an artifact that harms me, or simply one that I end up having to throw away and buy something new, that sort of waste is a harm, even if it's just a small harm. Money, obviously I've already mentioned that we can talk about the harm in money. So whether that is in trying to fix whatever problem there is. So when I purchase an artifact, or an artifact is designed in such a way that it's costly to produce, when it's costly to use, when it's costly to fix, or when it causes harms that then someone has to be compensated for. All of these cases, money can come into the picture as well as a form of harm. Repair costs. So as I mentioned in previous lectures, the idea that when you create an artifact that has a very high repair cost, or one that in fact can't be repaired at all, that then leads to other sorts of concerns. So when I can't repair something, that there is no repair cost, but there's the cost of the artifact itself, or the cost to purchase a new artifact. Storage, how long can an artifact remain intact before it goes bad? So there's certain chemicals that will only last a certain amount of time, devices that may wear out, things that have to be held for a period of time. And we might say, well, okay, storage costs can harm. They can harm in terms of lost profit. They can harm in terms of the byproduct. So if we're talking about nuclear engineering, storage costs matter, right? So what are we going to do with the spent fuel? Well, we have to store that fuel. Well, how much is that going to cost? Is there a danger to the storage? Does the storage have to be so well regulated and so specific that this is going to add a harm in some sense, or has the potential for causing harm? And the disposal, right? So what happens to an artifact after it's used? Do we think about what happens at the end of life of products? More and more, this is becoming an issue. If you look at companies, especially, for example, the electronics industry, where we're cycling through phones every 2 years, and for some people, it's every year. What do we do with all those phones? And are those phones manufactured in a way in which the parts of the phone, at least some of the material, can be recycled or reused? When that's not the case, then that stuff ends up in landfills. And again, we have another sort of social harm and environmental harm. Finally, The study of engineering ethics can help us when we ask the question of what counts as a solution. Maybe a better way to say that is what counts as a morally appropriate solution or a morally justified solution. So when we're looking at engineering ethics, engineers should should not strive for solutions that are simply minimally competent. So we can think of engineers or the practice of engineering as sort of a continuum. On the one side, we have the idea that what we minimally want to do is avoid error-provocative designs. The other side, though, or the other extreme, is that we should be looking for or striving for foolproof designs in engineering. So error-provocative is the minimum standard that we want to meet, whereas foolproof would be the ideal, that we could design an artifact in such a way that nothing could possibly go wrong with it, right? That we could avoid operator error and circumstances and so forth, all the things that we've talked about in the course. So engineers should be striving for the foolproof, not just for error provocative. In a similar way, the minimum sort of moral standard that an engineer should meet is to do no unnecessary harm. At the other extreme, of course, is something like strive for the best. So while morally speaking, I want to at least minimize my harm, the best I could do is to strive for the best possible design. One which caused no harm would be the ideal. Of course, we may never reach these ideals. It's not as if it may be humanly possible to create something that is 100% environmentally friendly, energy friendly, recyclable, and so forth. All those sort of things that we look for in a really good design. But it's still worth striving for. And that depends in part on the character of the engineer. So by simply pointing out how things can be done better, by studying ethics, by studying case studies, the examples that we've seen throughout the book that we'll continue to see, it shows us how we can do better as engineers from an ethical standpoint or a moral standpoint. And in fact, I think it makes for better engineers in general. I think it makes for more elegant solutions to problems. When I teach logic, I often say to students, there are any number of ways you can come up with a conclusion. You can prove a conclusion. So step by step doing a logic proof, you can get to a conclusion. I said, and one student once asked me, well, actually students ask me all the time, well, is there a right way to get to the answer? And I said, well, no, there's no right or wrong way. As long as all the steps are justified and you come to the conclusion, then that's an acceptable proof. The proof is correct. I said, but there are more elegant solutions. Some solutions are more elegant. So for example, in logic, elegance might mean less steps involved. If you can do the minimal amount of steps to get from premises to conclusion. The same can be said of engineering. There are any number of solutions for an engineering problem. So I know what the outcome is. I know what the desired goal is. I want a device for removing food from my teeth, or I want a device that closes a trunk lid, or I want whatever, a navigation computer. But when doing so, there are a number of different ways I could get to that solution, and some are more elegant than others. And this is something that I think just simply the experience of thinking about the ethical aspects of engineering can simply help engineers be better. Not only from the minimal standpoint of avoiding error-provocative designs and not doing unnecessary harms, to the sort of ideal of creating foolproof artifacts and striving for the best, striving to be morally the best in one's engineering practice. So engineering imperatives revised. And here I just want to sort of go over, summarize all the different aspects of engineering that we've talked to up this point. And much of the class that remains will be sort of fleshing out some of the details of these things. So we still haven't really talked much about what exactly a harm is, or how we determine acceptable amounts of harm. What counts as a morally appropriate design solution. We sort of hinted at these things, we've given some things, but we'll develop these in the remainder of the course. For now, I just want to sort of go over what the imperatives or commands, the moral commands are of an engineer. So here I've sort of just sketched out little ideas. So engineering ethics has composed of design solutions and the morally appropriate design solutions. We have the idea of role morality, what our role as an engineer, what that requires of us. There are external considerations, so the role morality might be considered from an internal perspective. And then they're aspirational, which we sort of brought up here. The idea that engineers should aspire to more than just the minimum. So it's these four ideas that we sort of develop as sort of the core of engineering ethics. Role morality, external relations, aspirational, and design solutions. So with role morality, remember, we recognize that as an engineer, certain role-specific duties are taken on. For example, ensuring calculations are made correctly. At the very beginning of the class, we mentioned this is sort of the classic approach to engineering, but it's also true of most professions. The role-specific duties that you take as a person in a profession. Design solution, recognize the moral implications of design solutions and do no unnecessary harm. So again, through the study of ethics, we talk about design solutions. We talk about bad design solutions. We say, how could this have been done better? And not just better from an efficiency standpoint, but from a moral standpoint. External, recognize that holding additional positions, employee, manager, etc., may lead to ethical dilemmas. So sometimes you're not just an engineer. Sometimes you're a business person, and there might be a conflict between what's expected of you, even if those expectations are not moral, what's expected of you as a business person or as a manager, and what's expected of you by your profession as a professional engineer. And aspirational, right? So practitioners should keep up with the latest engineering techniques, understand how new materials can make for better solutions, be more than merely competent. One of the things that I think is true of professionals, or should be true of professionals, if you're studying engineering, then you should love engineering. You should love looking at engineering techniques, reading engineering manuals, seeing what's going on in your field. If you're not excited about your field, then it's unlikely that you will aspire to be a better engineer, that you'll keep up with what's going on in your field. So aspiration, the idea that you want to be more than competent, to get better at what you do, seems to be part both of professionalism, but also just part of what you choose to do in life in general. And so I think that when we want to keep this in sort of the back of our minds, that when we're becoming professional engineers, that what we should be aspiring to is becoming better engineers. Not just an engineer, but thinking to ourselves, this is something I want to do in perpetuity. This is what I want to do with my life. I want to be the type of person who continues to refine their skills, to get more knowledge about what they do. That should also be a part of engineering. That should be part, and this is in some ways very much a character issue. What kind of person do you want to be? And in this case, what kind of engineer do you want to be?